guys, welcome to Unit 4. We're going to start this unit with a review of a graph that you've seen before, and we're going to add a little bit more detail into it. So hopefully you remember seeing the potential energy diagram last unit that looks like this. And notice that this time we have some numbers on it over here. We're going to use this graph and do a little bit of math, and we're going to get more specific about what all of those parts are and how to actually calculate their values. So we have to review all the different pieces of this graph. First, there are the reactants, or the starting ingredients. If I looked on the graph, those would be located over here, right? They're the beginning pieces. So I want to figure out, well, in this graph, how much energy do the reactants have? So if I read over about where that is on the graph, in this reaction, the reactants have about 200 kilojoules of energy. That looks terrible. I'll have to do it neater. And so kilojoules will be the unit for everything on this graph. If you forget that, it is right here, so you don't have to memorize it. It'll tell you. Okay. At the end of the reaction is the products. So those are the things produced at the end. So in my reaction, I would find the products over here. If I wanted to read that amount of energy, so I'd go to the products and read directly across. The products in this reaction have about 350 kilojoules of energy. Okay, so we're taking the same pieces of the graph you knew before, and now we're trying to figure out the actual numerical values for them. Next, we have the activated complex. It's the halfway point of the reaction. Remember, that's always going to be at the top of this hill. So way up here is the activated complex. So same thing, I could figure out, okay, how much energy is there if I read over. The activated complex here should be the highest point, so it'll always be the biggest number. And in this example, that's 450 kilojoules of energy. Next was the activation energy. It's the amount of energy to get the reaction started. So that goes from the activated complex to the reactants. Okay, so activation energy is kind of the height here from the reactants up to the activated complex. That's activation energy. So we're actually going to do the math for that by doing this subtraction. So we're going to calculate what is the activated complex, and then we're going to minus the energy of the reactants. So go back, our activated complex was here. That's about 450 kilojoules. Minus the energy of the reactants, read over, is 200. So the amount of activation energy, the amount of energy to get this reaction started, is about 250 kilojoules by doing that subtraction. The last piece is the heat of reaction. Another way to read that, this triangle is read delta, so heat of reaction, or delta H, is the difference in energy for the entire reaction. So that would be found here between products and reactants. So the way that you're going to calculate is by subtracting those two things. You're going to do products minus reactants. So if I did that for this example, the products, remember if we read over at about 350, minus the reactants at about 200 equals 150 kilojoules. So same pieces of the graph, and now we just did a little bit of math with them. So now you've got another version of the graph on your paper. So let's go through and label all of the parts there. Reactants are still at the beginning, and products are still at the end. The top of the hill is the activated complex. The distance up that hill is the activation energy from the reactants to activated complex, and in between the products and the reactants is the heat of reaction. So because this graph looks a little different, all of these are going to have different numerical values. So let's see if we can figure out what they'll be here. So the reactants are at about 350 kilojoules. The products, if I read over, are at about 200 kilojoules. The activated complex is the top of this hill, so if I read over, that has about 450 kilojoules of energy. Now if I want to do the activation energy, I like to abbreviate this formula. It's activated complex minus reactants. So the activated complex is the top of this hill at 450 kilojoules, minus the reactants, which started at 350. So that means the activation energy here is 100 kilojoules. That's how much energy you have to put in to make this reaction go anywhere. And lastly, for the heat of reaction, this is products minus reactants. Okay, so products here, if I read over, they're at about 200 kilojoules. Reactants are at 350. 200 minus 350 is negative 150 kilojoules. It is okay to get a negative number for heat of reaction. You should not get a negative number for activation energy. So this one should always be positive, and heat of reaction can be positive or it can be negative, and we're going to talk about why in a minute. So you've got these two different versions of the graphs on your paper because one is endothermic and one is exothermic. So we need to review what those words mean. So endothermic, the definition is that the energy goes in. Remember, energy in means that you would add energy from beginning to end. Okay? This graph right above it is the endothermic graph. If you have an endothermic reaction happening in your hand, there's my beaker, I've got my reaction happening inside. If heat goes into it, then everywhere out here, there's not going to be any heat left. And so what you're going to end up feeling is cold, because the heat is going to leave your hand and go inside of the beaker. So you'll know that you're observing that if your beaker feels cold. The way that it looks, if I give it to you on a graph, is the products would be higher than the reactants. And notice that's what we have in this example. The products are up here and the reactants are up here. Because we've gone up, this reaction is endothermic. Another way that you might see it is written out in an actual chemical reaction. So here are my reactants, whatever they are, and I'm adding heat. Notice that heat is happening at the beginning. We are adding it in order to make the reaction happen. So it might literally say the word heat as long as it's on the reactant side. Now we also know from our graph that heat is represented with a certain amount of kilojoules, so they might literally write those kilojoules in the reaction as well. Same spot. Notice in both of these examples they're adding the heat or the kilojoules on the reactant side. Lastly, when we calculated the delta H for this reaction, it was 150 kilojoules. Anytime you get a positive heat of reactants, or a heat of reaction, or a positive delta H, you know that your reaction is endothermic. If you can remember that, then exothermic is just everything backwards. So exo means that energy goes out, or it exits, or it's being released. So if I think about that in terms of my beaker again, here's my beaker, my chemical reaction is happening here, the heat is going to go out. And so if your hand was next to that beaker, you'd be able to feel all of that heat being released, so it would feel warm or hot to you. The way that it looks on the graph is opposite. Here, the products should be lower than the reactants. That's what we have up here in this example. Products, reactants, we've gone down. We've lost energy. If we wrote it out in chemical reaction form, we would have some reactants and the heat would be produced. It would come out at the end, again making it feel warm. So it's the same kind of format. We could write the word heat or some amount of kilojoules, but here they're on the product side. In the endothermic version, they were on the reactant side. Lastly, when we calculated the delta H, it was negative 150, and that's fine. Whenever you have a negative heat of reaction, it indicates that your reaction is exothermic, that you have lost heat. Last thing to review for this graph is the effect of a catalyst. Remember, it lowers the activation energy, and that's good because it makes the reaction go faster. And so this graph should be already on your paper. So just to review, here are my reactants, the activation energy, we go up the hill, and then we end at the products. But a catalyst is a good thing, because I'm going to draw that in red. It starts the same, but it's a smaller hill to climb. I don't know about you, but if I had to go for a workout, I would much rather do that smaller hill. Lowering that activation energy is much easier and a shorter route to climb. Alright, that's it. Let me know if you have any questions.